All right, everybody. Welcome to Geology. We got a short one this week, segment 5, chapters 16 and 18. And I'm going to make it even a little shorter than that. I'm out of town on a quick emergency trip here. So I'm going to get 18 down to these 2 paragraphs. There you go. That's going to take some stress off of 18. And maybe the very first sentence, which will come up. And then we'll take a little bit of a look at this. We'll get through some of the basics and call it good. Oop, I went the wrong way. So what this is going to be about, Earth system change, which is going to lead us into climate change and the nature of how the greenhouse effect works. But let's start with just the first couple. Why is it useful to think of the Earth as a system? And this is one of the themes that's throughout the course I've tried to get us going on. The idea that we've only been here for a very short amount of time. All of human history has only been here for a very short amount of time. You and me, ridiculously short. And even all of the history of us discovering all of this, the history of science and geology is all very, very short. So how is it that we can look out the window at Lake Ontario or go up into the Adirondacks and look at a mountain? It's easy in our short experiences on this planet to think of those things as permanent and unchanging. In reality, yes, on very long time scales and on different time scales for Lake Ontario and for the Adirondacks, these things are part of a dynamic system, tectonically, climatologically, astronomically even. So understanding how it is a constantly changing thing, and particularly when we get to feedback loops, we'll talk about that real quick as well. And eventually, I don't think in this video, I think I'll do a separate one for climate change and greenhouse effect and fossil fuel use. But let's just focus on this first couple. So constant change in the feedback section right about here. So positive feedback, as long as we don't associate positive with good things and negative with bad things in this instance. This is more about how 2 variables may amplify a change. That's the simple way they say it here. May ramp up is a way I've always thought about it. And a simple one is with, say, the amount of ice in an ice cap on the planet. So that what ice is white, right? With the snowpack on it, it's very efficient at reflecting energy right back off into space. The energy passes right through the atmosphere, hits a white surface. Most of it bounces right back. So there's net, we'll say negligible, very low energy gain from those sunbeams that hit the light and then take off from that insolation. But what would happen then if we melt off some of that ice? If we melt off some of that ice, it exposes what's underneath, which is going to be darker in color and more ready to take that energy from the sun and gather it in, which means the planet gets warmer. And then if the planet's warmer, more ice melts, so the planet gets better at absorbing energy, which means it gets warmer, which means more ice melts, which means the planet gets better at absorbing energy. That ramps up. That continues and continues and continues. That's what positive feedback means. Again, not positive as in it's a good thing. It's not. But positive as in the variables accelerate and amplify that change. Or we do it backwards, and there'd be a negative feedback loop. If something changes, but then that change defeats the mechanism of the change, that'd be negative. So there's the ice one right there. All right. So understanding how this changes these long-term things and understanding the basics between the difference between weather and climate without getting too nitty-gritty. Weather, this is going to be like what it's like tomorrow. Climate has more to do with, and this is another problem with us only living a certain amount of time. We only have so much data on gathering what our climate looks like. A lot, and enough to make some pretty good inferences about what's going on, but not necessarily like thousands and thousands of years worth of climate data that we've directly observed. We've been able to figure some out from ice records, glacial records, sediment records. But climate would be more of the large, longer term trends that determine what an area is like. Why? Look out your window. Why is Oswego like that? That's the climate that Oswego is situated in. Not this November's warm. That's has more to do with time-wise local weather patterns. So changes that can happen to these systems, and we'll mention this quick. Now, I'm not going to put anything about eccentricity or obliquity or precession directly on the test, but thinking about this spaceship that we're on, that we're hoping to preserve for future generations, the Earth, has these cycles where these things can very slowly change through time. How round the orbit is, what our tilt is relative to the orbit that we spin around, the tilt of the Earth's axis, which gives us our seasons. Right now we're pointed right at Polaris, the North Star. But go back to the Egyptians, they had a different one. Jump into a time machine and go 10,000 years forward, they'll have a different one. The Earth wobbles around a bit and its tilt changes. Now that's like spinning a top. If you spun a top when you were a kid and you saw that it starts to like slowly wobble, our spinning planet does just that. And with those changes, if you plot them all out, and this looks intimidating, I realize, don't panic about it. We won't be doing any numbers with this and we'll get too specific, but conceptually, if you plot this out, they've figured out why is it that in Oswego, again, look out your window, if you were here until about 10,000 years ago, say 12, 13, 14, 15,000 years ago, not that long geologically, you would have been looking out the window at a mile thick sheet of ice on top of the building. The building wasn't there, by the way. But what presently is Oswego was covered with this ridiculously thick sheet of continental ice in the Ice Age. So how do all of those changes, minor changes, even in astronomical, whatever you want to call these variables, how do they give us things like an ice age and then things like this interglacial period that we happen to live during? Now, what will be interesting, though, is where do these predictions give us what we had for a climate? And let's say humans never evolved and there was no technological organisms on this planet whatsoever. It was visited by a spaceship and they figured all this out, right? What difference between that planet and the one we have now, because we've gone to the planet and dug out significant amounts of different materials, which is basically what chapter 18 is about. Again, 18.4 is going to be the only one that I really go at. But the very first chapter of this, very first sentence, if you can't grow it, you have to mine it. Where have we gotten the stuff that this computer right here is made out of, or the one that you're looking at it on, or this lamp, or a pen? These things all had to come from somewhere. And if it's not made of plants, if it hasn't grown, it had to be mined, right? So and never mind the mining of materials we use to produce energy, to manufacture all those things and drive them around, right? So how would all of these cycles look with or without those effects? And I mean, the record's pretty clear. It's pretty blatant what has happened. Lastly, let's just quickly talk about this. There's this heat. Yeah, this guy. Thermohaline circulation. Now, if my map is still up, when I was in high school, a long time ago, I got to go to Ireland. And we got out. We stayed on the west coast over here. We got out of the car at the first place I stayed, and there in the front yard of it was a palm tree, which I did not expect. Now, look at Ireland's latitude. If you go straight over to like an equivalent latitude, which means this equivalent basically amount of insolation, you're talking up here. Where we live is down here, and it's already cold, right? Go way up here. You think you're going to be finding any palm trees up here near Hudson Bay? No, you have to go way, 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 way down here to do that. So how is it that I got out of the car and saw this palm tree? Now, note being, they're not native. They were transported in. It's just that they can be planted outside and survive. And the reason is because there's these giant belts, bands of water that carry energy from the warmer equatorial region out towards the polar region on the surface. It's plottable. I mean, you can look up these maps and see where it's at. Like people that fish up here will look at it day to day and see where this like belt of hot water, warm water, is working its way up the coast. And what happens is it comes right across and heads over towards Europe. So the west coast of Ireland there, although it's that cold, that north is capable of having palm trees live. I guess they can survive pretty much if it doesn't freeze, which it doesn't there because of those currents. Really vital to the economy of Europe over here, because if they were as cold as these guys were, you can forget about a whole lot of commercial shipping, which would make for a totally different Europe, right? So we really depend on this transportation of heat working its way up the coast. There's evidence of it changing presently through time associated with the climate change that we observe. And this is it in red right here. So it comes up, there's some circulation in the Gulf, but all of this, the heat that's gathered near the poles here, near the equator here, goes right up the east coast of the United States and then shoots its way across to Europe. And from what I've gathered, the concern is that if there's too much cold or fresher water coming in down here, it could cut that off. And if that does, very bad news for Europe. Now it's like a belt has got to return, but the ocean's deep. It can come back around, and you get these very large conveyor belts, like three-dimensional conveyor belts through the ocean, caused by thermohaline, would refer to temperature and salinity differences. Differences in salinity make for differences in density, which can drive these things. So we have that to thank, again, for this whole area being the way it is, and other areas too, but this just because of that palm tree struck me when I was growing up, right? We have those currents to thank for this area being the way it is. And since I'm going to live somewhere between 43 and let's say 200, I'll be greater than 43 years old next week, and I'll probably exit this earth before I'm 200, right? No matter what, that's still a very short amount of time. To look and say, just take it for granted that this area is like this. Now that we've started to unravel the systematic reasons that make the planet operate the way it does, we must also unravel ways to understand how to preserve those and understand how to get the public on board with the idea that there's certain behaviors we have, habits we have, methods of efficiency we have that could be improved in order to preserve some of this. Which we'll jump into a little bit more when we get to carbon cycle. That'll be the next video. Hope everybody's doing okay. We'll talk to you soon.